Hello, my name is Slava Novgorodov. This is a joint work with Shay, Gershtein, Avron, Guy, and Tova Milo. The name of this paper is Automatic Category Tree Construction in E-commerce. This work was done while it was at TB Research. So today I work for Facebook, but this is like a previous work from a previous place, from previous job. So what is the motivation for this paper? As you probably know, if you once shopped on online e-commerce platforms, category trees play a central role there because they enable a browsing style information access. But building those category trees is very hard task because it's mostly done manually by in-house taxonomists. So we are trying to somehow automate this construction. Okay, so what we are doing, first, let's formally define what is the category tree. So let's call category tree is a rooted tree where every node is a category of items. So what does it mean? Every category contains the union of its descendants, and every item appears only in a limited number of branches. In most cases, it appears only in one branch. What I mean, so if, for example, you have a Samsung phone, it will be under the Samsung category, which will be under the smartphones category, which will be under the electronics category. So this is what is usually done when you're talking about placing some product under some category in the category tree. What is the input for our problem? So as I said, we were trying to build automatically build those category trees. So what is the input? So we are assuming that we have a set of sets of elements that user may wish to find in the tree. Okay, and each set has its own weight, which reflects the importance of this specific set. This importance can be derived in many ways. We will talk about it in a few slides. But for now, the idea is to build the tree in such a way that for each of these sets, we have a specific category that contains this specific set. So if we have much more items than this subset, which did more than this specific set, it's not so good. So we want to have as precise as possible sets that represented in the tree. Okay, how we derive this problem, how we translate it to the e-commerce application. So in e-commerce, we have a lot of queries, search queries, and we can use the search query results as the input sets because those search queries are identifying the user interest. So for example, if you have a lot of queries like shirts or Adidas shirts or black shirts, you can use this information in the subset of items that is returned by the search engine as the input sets for this problem. And the frequency of how many times these queries are searched by the user. So for example, if black shirt is a very popular query, then it has a higher weights in terms of the input set weight. So in this case, you can see an example of Adidas Originals black shirt query. And here is the result set. And you can see what we are expecting to have it in the tree. So we're expecting to have like a fashion category. Under the fashion, we have shirts, Adidas, Originals, which is a collection. And then you have the color black. So this is one possible tree. Of course, we can have many other possible trees, but this is one very logical possibility. Why the problem is so important and why we are trying to have specific category for each of the possible interesting input sets. So assume you have two different category trees, the original category tree and the tree suggested by our system. If you have a query man shirt, it doesn't matter which of the trees can, so both trees can return good results for this query. In the left tree, which is the original category tree, you can go to fashion, men, and shirts. So this men shirt will be here. And in the suggested tree, you can go to fashion, shirts, and then men. And it will contain mostly the same set of products. But if you have a query shoes, so in the suggested tree, you have a good category for shoes under fashion. But in the original tree, since the fashion is divided into men and women fashion, you don't have one specific category that contains both men's shoes and women's shoes. Hence, you cannot return one specific category, which is very precise. And instead, you need to return maybe the whole fashion category in order to help the user find relevant information. Same as for another example of memory cards. So assume that you have the memory card query. In the suggested tree, you can go under the memory cards category under electronics. But in the original tree, since you have the division between memory cards for cameras and memory cards for phones, which are mostly the same types of products, okay? So, and they are just divided, historically divided into two categories. You cannot return one specific category, so probably you'll need to return the whole electronics category. Okay. Formally, when we're talking about problem, as I said, we have a set of weighted sets of elements, and we have the weights, and we have different problem variants. What I mean by problem variants, so we have different similarity functions. What is the similarity between the tree and the input set? So, for example, in this case, we are giving a score for a tree based on the input set. So in many cases, we will call these input sets just queries, because it's in our specific case, those input sets are derived from search queries. So how good this tree covers the query is just the maximum between the similarity of the set of queries, of the elements in the query, and the specific category of the tree. So if there is a good category that covers this query, we are good. Otherwise, no. And the score of the whole tree is just the score of each query from the set of queries. So this is definition, and this is the sum of weights of queries multiplied by similarity of each individual query. Because as I told you, each query has its different. So each input set, which is in our case query, has its own different weights. So it's very important to follow the weights and to give more priority to more important input sets. And our objective is to build a tree that maximizes this score. Okay, in terms of the similarity functions, we have the usual F1 score. We also have Jacquard, threshold functions, cutoff, perfect recall, and other variants. We also have a special case of exact variant, which is a binary. So you will need, in the exact variant, you will need to cover the input set in the whole. So you need, if you have a category that contains exactly the same set as the input set that you were given, so it's okay, you were getting 1 is a score of 1, otherwise you are getting 0. So it's a binary function of exact match between the input set and the specific category in the tree. Of course, you can do some threshold relaxations for different functions. So for example, if you're using Jacquard similarity and you have these two different sets, set 1 and set 2 of those elements, and you are building this tree, so you have category 1 and category 2. So you can say that category 1 covers the set number 1 because the similarity is 0.8, because it has 5, the set has 5 elements, but the category contains only 4, so 4 out of 5 it's 0.8, which is good enough because our threshold is 0.7. So you will get the score of 1. Otherwise, if the similarity is lower, so in this case, the similarity is only 0.6, so it doesn't cover, and because it's below the threshold. So this is, again, an example of different similarity function. More details about the similarity function and their adaptation can be found in the paper. Okay, so let's look into quickly into examples. So you have 4 different queries of different weights. So query number 1 is the most important, and the other have equal importance of 1. You can assume that these elements A, B, C, D, E, etc., are just shards of different brands, different colors, and different sleeve lengths. And here, the queries, you can assume that those queries are black shirt, black Adidas shirt, Nike shirt, and long sleeve shirt. So this is exactly the elements that will be returned. And you have only 9 elements, but this is just a demonstrating example. So it's very small, just to demonstrate the operation of the algorithm. So one of the possible solutions that you can get is this tree. What this tree resembles? It just shows you that you can divide the shirts into Adidas and Nike, which can be further divided into Adidas and Nike separately. And in the other branch, you can have all other brands. This one solution. Another solution can be this tree, and the difference is not very big, but in this tree, what you're getting is shirts divided into black and other colors, and once you're going into black, you have the long sleeves and the short sleeves. So this is another possibility for a tree. And each tree has its own score based on the all 4 queries that we are showing here, and based also on different similarity function that we are calculating. So this is just an example. So there is a lot of types of division of the products into different trees. So in this complete paper, we are based on our theoretical results from our ICDT 2022 paper. We showed that all different variants of the problem of different similarity function are very hard. So this is like NP-hard solution, and NP-hard problem, and the solution is inapproximable. So we cannot give any good approximation for different variants. We are showing like we have a detailed proofs for each of the variants in the ICDT paper. So since we have this problem with the hardness, we decided to use heuristic algorithm for different variants of the problem. We have different heuristics. So in this paper, we are talking about the solution of these problems. We're proposing a couple of algorithms. I will show only two, but we have much more in the paper. So if you're interested in the more details, you should look into the paper. So one algorithm which is used for the exact variant is based on the MIS problem, which is what is MIS? So MIS in the maximum dependency problem, and the idea is given a graph to find a largest subset of nodes that has no edges between them. Okay, so it will be an independent set. And how we use it? So we define something called query conflict. So what is query conflict? We say that two queries in a conflict, if they are neither disjoint and neither one contains the other. So they're actually in conflict. That means that there is an element that is shared between two different queries. So we need to decide which of the queries we can cover in order to get the maximum possible score. And how we use it? So first we take all the queries that we have. For each query, we put a node. We build the graph. We put the node for each query, and then if two queries are in conflict, we are building an edge between them. And then based on this graph, we are running the maximum dependent set heuristics algorithm, which are very good in practice, and getting this nice tree. So this is one solution, as you can see here. Like this is the process of building the graph and then running the MIS heuristics and getting this rooted tree. Another option that we also have is based on embeddings. So we can build different embeddings for the products. Then you use bottom-up clustering algorithm. And then after we're building the structure, we can do the item assignment, which is also another solution. Again, more details in the paper. What is the difference? When is better to use one and when is better to use the other? We compare their performance. All the details appear in the paper. Just want to show you two more things. So first is the experiments. We tested our algorithms on different types of data sets, on different both publicly available and private data sets. We show that our algorithm achieves the best scores compared to its competitors. And we also show that our algorithm is very scalable. So even for larger data sets, you will need to wait not too much time. So it's, let's say, half an hour for like very big data set. And then you are building a tree, which is compared to the manual construction, it's much, much faster, because if you're constructing this tree manually, you will need to invest a lot of time and a lot of effort of your in-house taxonomist in order to build the trees. So that's it. I hope you enjoyed the paper, the presentation. And if you have more questions, so you are welcome to ask now or send an email afterwards. And of course, I invite you to read our paper for more details. Thank you very much.